September 23, 1999. Controllers are glued to their monitors, intensely tracking the carrier signal of a spacecraft that's rapidly closing the distance to the red planet. I mean, this is it. The absolute culmination of a 9-month, multi-million-dollar journey from Cape Canaveral.
Right at 0952 UTC, that vital carrier signal just abruptly flatlines. The spacecraft slips behind Mars, and this interruption, well, it's actually completely expected. It's a maneuver called occultation, where the planet physically blocks the radio path back to Earth. So the controllers just sit back to wait out the silence. But the minutes tick by. The anticipated return window opens and closes. Tracking stations sweep the void, literally straining for just a whisper of data. But nothing arrives. The Mars Climate Orbiter, which was designed to be humanity's first interplanetary weather satellite, never emerges from the shadow of Mars.
So how exactly does a massive spacecraft vanish without a trace? We have to rewind 9 months to the December 1998 launch. And here's a detail that is just wild, something you definitely wouldn't see coming. In the utter vacuum of space, you really wouldn't think sunlight could push a heavy probe off course, right? But sunlight hitting the spacecraft's asymmetrical solar ray acted exactly like wind catching a sail. This constant uneven pressure was steadily adding rotational momentum to the craft's reaction wheels. To counter it, the onboard systems fired these small thrusters to unload that momentum. It's a process called angular momentum desaturation, or AMD. Planners thought these AMD events would be super rare. Instead, real-world physics forced those thrusters to fire roughly 10 to 14 times more often than anyone ever anticipated.
Now, every single time those thrusters fired, they imparted a tiny physical change in the spacecraft's velocity. To keep their digital trajectory models perfectly lined up with the spacecraft's actual physical path through space, navigators desperately needed accurate impulse data. But there was a fatal flaw just hiding in plain sight. Lockheed Martin, the company that built the spacecraft, ran a ground program called SM_forces to calculate this impulse data. And they programmed it to output the forces in pound-force seconds, which is the customary United States unit. However, the Jet Propulsion Laboratory, JPL, who was managing the mission operations, had a really strict interface specification. Their software absolutely required metric Newton seconds.
Okay, so the number 4.45 becomes absolutely crucial here. It's basically an invisible poison in the system, because 1 pound-force-second equals roughly 4.45 Newton seconds. But when Lockheed Martin's software beamed its data over to JPL, the file just contained ordinary-looking numbers. There was no automatic unit marker attached to them, no digital warning label that would trigger a rejection, so the JPL receiving system just obediently digested those numbers, totally assuming they were already metric. The immediate, terrifying result? Every single modeled thruster impulse was dangerously understated by an exact factor of 4.45.
And this didn't stay a single, isolated math glitch. Oh no, it built into an unstoppable chain reaction. If those thruster unloadings had actually been rare, like originally planned, this unit mismatch might have just been a harmless little quirk. But remember that asymmetrical solar array acting like a giant sail? Because the actual physical spacecraft was constantly fighting solar pressure and firing its thrusters 10 to 14 times more often than expected, the math errors didn't just happen once, they continuously multiplied. Completely unchecked by any software boundary, real-world physics just kept amplifying this mathematical phantom, causing a persistent, accumulating drift in the actual trajectory.
Which brings us to another massive surprise. People actually knew something was wrong. Working-level navigators were totally noticing these weird Doppler residuals. Basically, the Doppler data, which tracks the spacecraft's line-of-sight motion from Earth, was simply not matching the software predictions. But the mission was caught in this totally chaotic transition into flight operations. Faced with staffing constraints, uncertain responsibilities, and honestly limited familiarity with the spacecraft itself, the navigators' concerns just never solidified into a formal anomaly report. Instead, these massive red flags remained trapped in informal chats and scattered emails. Meanwhile, these highly precise-looking estimates kept churning out of the software, completely masking the reality that their foundational force input was compromised.
By the time September 1999 approached, the orbit determination showed the probe coming in far lower than intended. This wasn't some sudden swerve, it was the sheer weight of thousands of tiny, miscalculated impulses finally showing their hand. A late emergency burn, known as Trajectory Correction Maneuver 5 or TCM5, was literally on the table. It was their final out. But a system completely paralyzed by divided responsibilities, uncertain orbit estimates, and rapidly shrinking time simply couldn't pull the trigger. TCM5 was abandoned. Unbeknownst to anyone in that control room, the true trajectory was already drifting roughly 170 kilometers lower than their planned safe passage.
The spacecraft fired its main engine for orbital insertion exactly as commanded, blindly following a pristine but entirely fictitious digital path. Post-encounter reconstruction eventually ripped away the math to reveal the brutal physical truth. The error placed periapsis, the lowest point of the approach, not at a safe orbital height, but at an unrecoverable 57 kilometers. It was far too low to survive atmospheric entry. All the data tracking, the incredibly complex software files, and the months of transit just ended on a final calculated chart. A thin approach line meets the shaded Martian atmosphere only 57 kilometers above the rust-colored surface.